Okay, let's take a look at quiz number 6. For number 1, we've got this chemical equation that's given to us in the problem. We've got hydrogen reacting with nitrogen to make ammonia. And we are also given that we have 1.39 moles of hydrogen gas and we have 3.44 moles of nitrogen gas. And the question asks, how many grams of ammonia do we make? So the first step to any kind of problem like this is that we always have to determine the limiting reagents. We need to determine the limiting reagent. So the way we're going to do that is we're going to start off supposing that we have 1.39 moles of hydrogen and an unlimited amount of nitrogen gas. How much ammonia are we going to make? So we've got hydrogen here, and we've got 1.39 moles of it. And now we have to figure out how many moles of ammonia do we make. So we use the mole to mole ratio, so we've got 3 moles of hydrogen being consumed to make 2 moles of ammonia. So we have 2 moles of ammonia that are produced when 3 moles of hydrogen are consumed. Moles of hydrogen cancel, and now we're in moles of ammonia. And what does this give us? It gives us 0.927 moles of ammonia. Okay, let's take a look at nitrogen. So we're given in the problem that we have 3.44 moles of nitrogen. And once again, let's return here to the balanced equation. For every 1 mole of nitrogen that is consumed, we make 2 moles of ammonia. So let's put that in our equation here. We make 2 moles of ammonia when 1 mole of nitrogen is consumed. Alright, moles of nitrogen cancel, and once again we're in moles of ammonia. So that is going to equal 6.88 moles of NH3. So from these two, we want to figure out which one of these is the limiting reactant. Well, clearly here, the hydrogen, let me circle that, the hydrogen is going to be our limiting reactant. The reason why is because we run out of ammonia first with the hydrogen. So hydrogen is the limiting reactant. All right. So now that we know that hydrogen is the limiting reactant and we know how many moles of ammonia we make, and we can say, okay, well, if the question is asking how many grams of ammonia we produce, and we know the moles, then we just use the molar mass of ammonia, and that gets us from moles to grams. So let's go ahead and do that. We've got 0.927 moles of ammonia, and each mole weighs 17.031 grams. So now our moles of ammonia cancel, and we are left with grams of ammonia as our units. And this number, by the way, I just got from the periodic table. So this means that our mass of ammonia that we produce turns out to be about 15.78 grams of ammonia. And that rounds to 15.8 grams. Okay? So the correct answer for number 1 is B. For number 2, we're given this chemical equation where calcium carbonate, or lime, is reacting with hydrochloric acid to make calcium chloride, water, and CO2. And we're also given the masses here of the lime and the hydrochloric acid. And the question is, how many liters of CO2 do we make? So let's remember here that in order to have liters, we need to first calculate how many moles of CO2 we make. and then we have a unit conversion that's given to us in the problem, which we'll get to at the very end when it matters. So in this problem, we've got 2.35 grams of calcium carbonate. And what we have to do is convert this into moles. So in order to do that, we just have to visit the periodic table and say and look up what the molar mass of calcium carbonate would be. What we would find is that 1 mole of calcium carbonate weighs 100.1 grams. So our grams cancel, and we have moles of calcium carbonate. So what that gives us is 0.0235 moles of calcium carbonate. Then the next thing we have to do is figure out how many moles of hydrochloric acid do we have. So let's go ahead and do that. It's the same thing, 2.35 grams of HCl times, for every 1 mole of HCl, there are 36.46 grams of HCl. Okay, our grams of HCl cancel, and we are left in moles of HCl. So how many moles do we have? It's just 0.0645 moles of HCl. Okay, so we're not quite ready to determine which one's our limiting reactant, but we're almost there. We have moles. Now we have to figure out, okay, there's this many moles of calcium carbonate and this many moles of HCl. How many moles of CO2 are we going to make? And in order to do that, we just set the problem up like we've always been doing, where we keep in mind here that let's go ahead and do calcium carbonate first. We've got 1 mole of calcium carbonate that is consumed to make 1 mole of CO2. So our mole to mole ratio here is going to be 1 to 1. So let's keep that in mind here as we do calcium carbonate. We're going to take a look at calcium carbonate, and we have 0.0235 moles of calcium carbonate. And we have to go to the balanced chemical equation, and if you remember, we found that 1 mole of CO2 was produced when 1 mole of calcium carbonate was consumed. Moles of calcium carbonate cancel, and now we have moles of our product, which is CO2. So when we perform this reaction, we make 0.0235 moles of CO2. Okay, so that was the calcium carbonate. So let me just label this here as finding the limiting reactant. That's what we're doing here. So this is our calcium carbonate, and now let's take a look at our HCl. So going back here, we found that we have 0.0645 moles of HCl. And let's go back to our chemical equation. Our mole to mole ratio here is 2 to 1. We have 2 moles of HCl consumed for every 1 mole of CO2 produced. So we need twice as many moles of HCl to produce a mole of CO2. So we're going to come back here and use that mole to mole ratio. So we say that for every 1 mole of CO2 that we produce, we consumed twice as many moles of HCl. There's a 1 to 2 mole ratio there of CO2 to HCl. Now our HCl moles cancel, and we are happily left in moles of CO2. So what this gives me here is something I gotta plug into my calculator. So I've got 0.0645 divided by 2, and I make 0.03225 moles of CO2 with my HCl. Okay, so this was our calcium carbonate, and this was from our HCl. Which one is our limiting reactant? It's going to be the calcium carbonate, right? Because we have made less CO2 with the calcium carbonate than we did with the HCl. So what we find here is that the calcium carbonate is the limiting reactant. So just like before, now we've done most of the work at this point because we've determined the number of moles of CO2 that we produce with our limiting reactant. Now let's go back to the question and see. We see here that all the answers for the multiple choice are offered in liters, so we have to convert our moles into liters. And that's where I said we'll get to this at the end. Well, we're basically at the end, right? So we have moles, and then the problem gives us a conversion that takes us from moles into liters. And that conversion is that for every 1 mole of CO2, we occupy a volume of 22.4 liters. So let's go ahead and show that. We have 0.0235 moles of CO2, and we're just going to do a unit conversion that takes us into liters. So there are 22.4 liters of CO2 in a mole of CO2. Moles of CO2 cancel, and we are in liters of CO2. And when we do this, we will find that we made enough CO2 to take up 0.526 liters. And that corresponds to C. So the right answer for number 2 is C. Number 3 seemed to be a little bit tricky because it was a little bit unclear as to what the mole-to-mole ratio is here of acetic acid and isopentyl alcohol reacting to make isopentyl acetate. So, yeah, I apologize for that. I see where a lot of the confusion came from. I think that it is fairly okay to make the assumption, however, that that acetic acid and isopentyl alcohol will react with a 1-to-1 mole ratio with isopentyl acetate. So you'll make, for every 1 mole of acetic acid you consume, you're going to make 1 mole of isopentyl acetate. And then also for every 1 mole of isopentyl alcohol that you consume, you're going to make 1 mole of isopentyl acetate. So everything is just a 1-to-1 mole ratio. I hope that wasn't too confusing for you. I apologize if it was. So let's go ahead and work through this problem and just keep in mind that everything here is a 1-to-1 mole ratio. Okay, so the problem gives us this reaction, and it gives us the mass of acetic acid and the mass of isopentyl alcohol. And it asks us to determine what the percent yield of the reaction is. It also tells us that the mass of isopentyl acetate that we have is 2.96 grams. So what is this mass? It's just if we went to the lab and we performed this reaction and we purified the isopentyl acetate, what we would get at the end of the day is 2.96 grams. So this, in other words, would be your actual yield. Your actual yield. So we're going to come to that at the very end. So the question, first of all, is what are we trying to accomplish here? Well, we want to figure out what the percent yield is, and in order to find the percent yield, we have to determine what the theoretical yield is. Because if you remember, percent yield equals the actual yield in grams, in this case, divided by the theoretical yield, also in grams. And of course we'll do this to be technically correct because it's a percent. Anyway, but the important thing is that we've got an actual yield and a theoretical yield that we need in order to calculate percent yield. So we have our actual yield that's given to us in the problem. What we have to figure out is this. What is our theoretical yield? So let's go ahead and start out doing this by by figuring out which of the reactants is our limiting reactant. And we're going to do this exactly the same way as we've done all of our previous problems. So let's start out with acetic acid, and here I went ahead and converted it into moles already. I just did this from the periodic table. The question gives you the chemical formulas, and so you just look up the atomic masses on the table and you get these moles. So we've got 0.0311 moles of acetic acid and 0.0262 moles of isopentyl alcohol. So from here, we just need to figure out which of these is our limiting reactant. So let's find the limiting reactant. Right, this is really important because we need to determine which one we're going to run out of first. So if we look at the acetic acid first, I understand this is going to become really obvious, but it might already be obvious to some people, but I'm going to go ahead and be really systematic here and write everything out. So we got 0.0311 moles of acetic acid, and then we have a 1-to-1 mole ratio of our product here, isopentyl acetate, and 1 mole of acetic acid. So the moles of acetic acid are going to cancel, and we're going to be left in units of moles of isopentyl acetate. Well, of course, why I said this would everything would be here really obvious is because everything's just a 1-to-1 mole ratio. So of course, if we just take 0.0311 moles of acetic acid and we convert it with a 1-to-1 mole ratio into moles of isopentyl acetate, we're going to end up with 0.0311 moles of isopentyl acetate. Okay, so that was our acetic acid, and we can do the same thing for our isopentyl alcohol. So we start with 0.0262 moles of isopentyl alcohol. And we have 1 mole of isopentyl acetate. For every 1 mole of isopentyl alcohol. Okay, so all I wanted to show here is that the moles of isopentyl alcohol cancel, and we are left in moles of isopentyl acetate. And once again, since it was a 1-to-1 mole ratio, it's clearly 0.0262 moles of isopentyl acetate. So which of these is our limiting reactant? It's going to be the one that gives us the least amount of isopentyl acetate, because that's the one that we're going to run out of first. So this would be this one right here. This is our limiting reactant. And so the limiting reactant was the isopentyl alcohol. Okay, so if we have now the number of moles of product that we made, that's the 0.0262 moles of isopentyl acetate, then it's fairly straightforward to convert that into grams. So let's go ahead and do that. 0.0262 moles, oh, now I have to write it out again, isopentyl acetate, it's okay. And our molar mass here is just going to come from the periodic table. So I'm going to look it up here. The molar mass of isopentyl acetate is going to be 130.19 grams. And I'm not going to worry about writing it out. Yep. So 1 mole here and 1 mole there. Or moles and moles cancel. And now we're left with grams of isopentyl acetate. And if we do this, we would get 3.41 grams of isopentyl acetate. That's our product. Okay, so we have now the theoretical mass of our product. So now let's go back and figure out what the percent yield is. So let's remember that percent yield is the actual over the theoretical masses. So our actual, back at the beginning of the problem here, the actual yield was 2.96 grams of isopentyl acetate. That's 2.96 grams. And the theoretical yield was 3.41 grams. 3.41 grams. And if we do this out, we get 86.8%. And that corresponds to D. So the answer for number 3 is D. Number 4 asks us to determine what the percent composition is of urea. And here's the chemical formula for urea. And I went ahead and calculated the molecular weight of urea. It turns out to be about 60.1 grams per mole. Okay, so how are we going to go about doing this? Well, first of all, let's remember what percent composition means. Percent composition, when we're saying, say, the percent composition of carbon, for example, so we've got carbon in here, so we can ask, what is the percent of the mass of this molecule? What percent of that is carbon? So in order to go about figuring that out, what we want to first notice is that for every 1 mole of urea, there is 1 mole of carbon. So there's 1 mole of carbon in every 1 mole of urea. And how do we know that? We know that by looking at here. So for every 1 mole of this molecule, there's only going to be 1 mole of carbon. Okay, and how much does a mole of carbon weigh? Well, we get that just from the periodic table. It weighs 12.011 grams. So our moles of carbon cancel, and here what we're left with is 12.011 grams of carbon in a mole of urea. Okay, so if we wanted to figure out what the percent composition is, we can say, well, okay, this is 12.011 grams of carbon in a mole of urea. Then percent composition is going to be percent composition for carbon is just going to be the mass of carbon per the mass of 1 mole of urea. So I'll just say grams, I'll go ahead and make this in grams too. So grams of 1 mole of urea. That's all we're saying. How much of the mass of urea is made up of carbon? So we have here that a mole of urea has 12.011 grams of carbon, and so then all we want to know here is how much a mole of urea weighs, because we want a percent, so we want to make sure our grams cancel, our units cancel. So we get 12.011 grams of carbon. That's how much carbon we have in a mole of urea, divided by 60.1 grams of urea. So we're saying here that we've got 12.011 grams of carbon in 60.1 grams of urea. So our grams are going to cancel, and essentially what we're left with here is a percent. So we're going to find here that 12.011 divided by 60.1 is 0.19985 and so on, and that is going to be approximately 20%. So we have 20% by mass of carbon in a mole of urea. That's all it is. Okay, and we can do the same thing for the nitrogen and for the hydrogen and for the oxygen. And here we don't really need to, but we can go ahead and do the nitrogen. The reason I was going to say we don't really need to is because C is the only answer that has 20% carbon in it. But suppose that you were not absolutely sure, or suppose there were two answers that had 20% carbon in them. So in that case, you would have to do another one of the elements. So to exercise that, we'll just go ahead and do another one of the elements. Let's choose nitrogen. And for nitrogen, we have 2 moles of nitrogen in every mole of CH4N2O. Right? So we have a mole of this, and there's 2 moles of nitrogen and a mole of urea. That's where this came from. So we got 2 moles of nitrogen for every 1 mole of the molecule urea. And if we multiply that by grams of nitrogen, this just is the molar mass, or the atomic mass from the periodic table of nitrogen. And a mole of, it's the molar mass of atomic nitrogen, not molecular nitrogen, which is N2. I'm sorry, that was confusing. 14.007 grams of nitrogen are in a mole of nitrogen. That's what I meant to say. So our moles of nitrogen cancel, and now we're in grams of nitrogen. So if I do this out on my calculator, I would get 28.014 grams of nitrogen are in 1 mole of urea. So if we wanted to find the percent composition of urea that is nitrogen, what we want to do is we want to say, okay, 28.014 grams of my compound is nitrogen. What percent of the total mass is that in a mole? It's out of 60.1 grams of urea. And what that would be is 46.6% nitrogen. So that's how I'd go about doing that. All I'm saying here is what percent of the mass of my molecule is going to be nitrogen. And I pick 1 mole because I have the molar molecular mass, and I can figure out that I have 2 moles of nitrogen. So I just get that right here. 2 moles weighs 28.014 grams of nitrogen. I divide that by the molar mass of the entire molecule, and I figure out what portion of the molecule's mass is from nitrogen, and it's 46.6%. So that is going to confirm that the correct answer for number 4 is C. And then lastly, for number 5, we're looking here at a problem where we're trying to determine what the empirical formula is for ibuprofen. So we have here our percent composition. So here we have 75.69% carbon, 15.51% oxygen, and then 8.8% hydrogen. And I went ahead and wrote this out. So I said, suppose that we have 100 grams of ibuprofen. That's the way I like to go about these problems. And if we had 100 grams of ibuprofen, then 75.69% of 100 grams is going to give us 75.69 grams of carbon. So that's why 100 grams is really convenient, is because you have your grams already set up. So this way we've converted into masses of each of the elements. And then what we can do is convert each of these masses into moles. So let's go ahead and do that. So what I'm just doing is I'm going to the periodic table, and I'm looking up that 1 mole of carbon is going to weigh 12.011 grams. So my grams are going to cancel, and I will have 6.3 moles of carbon. So I'm just going to take a second here and go through all the rest of them, and we'll go from there. Okay, so all I've done is I've just converted all of these masses into moles for each of the elements, for carbon, oxygen, and hydrogen. So where do we go from here? Well, we can do with these masses, with these moles now, is we can take these moles and make them into a an empirical formula. So let's go ahead and start off with that. We've got 6.3 moles of carbon, and I'm going to stay consistent with how the problem is written. It does hydrogen first. So I've got 8.87 moles of hydrogen and 0.969 moles of oxygen. So we just get these numbers from what we calculated here. That's our moles of each element. Okay, and our goal is, now that we have this, our goal is to make all of these numbers integers. So we want to make all of them whole numbers, because you don't generally look at a chemical formula of water. Water is typically written as H2O, right? You don't typically see HO 1/2, right? Or O or HO 0.5. Okay, even though that might technically be true on a mole scale, where you could say, well, I've got half as many moles of oxygen as I have water. Where that breaks down is when you bring it down to the molecular scale. How do you say that you have 0.5 atoms of oxygen for every molecule of water? It just doesn't make sense. So you try to get everything into whole numbers like this so that you can look at that and go, oh, well, when I bring it down to the molecular level, I've got 2 atoms of hydrogen and 1 atom of oxygen for every molecule of water. So we want to do the same thing for ibuprofen. We want to see if we can get all of these numbers to be integers so that we can have whole number values in our empirical formula. So we've got here 6.3, 8.87, and 0.969. And the first step is to divide all of these numbers by the smallest of these. So we're going to divide all of them by the coefficient here that's with the oxygen. So let me go ahead and write that out. Okay, and then I'm going to divide all of these by 0.969. Okay, and what that's going to give me is, let me move this up a little bit so you can see. Carbon's coefficient now becomes 6.5. Hydrogen's becomes just about 9. They round, so you can round these up. And then oxygen becomes 1. So you might say, well, Daniel, here, so I got something very close to 6.5. Why don't you just round that up to 7? Well, and the reason why is because it's 6.5. This looks an awful lot like something you could just multiply the entire formula by 2 and make this into an integer. Had you rounded this up, it would not have worked as well. So let's multiply this entire molecule by 2. All these coefficients by 2 and see what we get. So what we're going to do here is we're going to multiply all of them by 2. So this becomes 13, this becomes 18, and this becomes a 2. So this looks like one of the answers. This is in fact the correct answer, and this is A. So I want to explain here why 6.5 doesn't just round up to 7. The reason why is because anytime you get something that rounds to 0.5, basically you have not reached your integer numbers yet. So anytime you round, you want to be pretty close to the number you're rounding. Like if this was a 6.9, that would have been okay to round to a 7. If this was like a 6.1, that would have been okay to round down to a 6. But because this is exactly 6.5, this indicates that we are not yet at the integer level. And so we need to make one more multiplication to get all of these into integers. And so we multiplied it by 2 to get the 6.5 into an integer. And by multiplying all of the numbers here, we got C13, H18, and O2. And that gives us the answer A. Alright, so that's quiz number 6.